the screen share is good. Okay. Great. Thanks for the introduction, Lisa. It's great to be here to talk about the chip we built in my startup. And this is obviously work done by a lot of people. And I'm really honored to have this opportunity to come and talk to everybody about it. Oh, sorry. Let me try and minimize this. Move this up here. Here's the overview of my talk. First, I will describe why we need a new architecture, and then explain what is the architecture that we built, reuse exposed data flow, and then some interesting things in the microarchitecture, software development process, and then how well the implementation does, our implementation Mozart, and that'll really lead up to these retrospectives that I want to share with everybody. Okay. So let's get started. Why do we need a new architecture? And I apologize for the whole blockage of stuff over there. So the context is, look at the business context of AI and beyond. That's the space that we were targeting. So there's a huge application opportunity. The applications are changing really fast. CNNs, DNNs, transformers. Every 6 months or so, there's a substantially different application behavior. Second, there's a business opportunity. There's substantially low GPU efficiency or utilization at small batch size measured in single-digit %, which leads to a technical opportunity that data reuse has been unexplored at the architectural level, even though it is pervasive across these workloads. So our technical contribution is an architecture, or the first architecture, that exposes reuse and data flow, while previous efforts have been largely implementations. And this builds upon a body of academic work that I was working on before founding the company. So that's why we want to do this. So what is the architecture? So reuse exposed data flow starts with this idea of a von Neumann core, to which we attach a compute data flow core and then a relatively small memory for on-chip reuse. This gives us a couple of things. Gives us the efficiency of data flow. With the von Neumann core coupled, it gives us a very simple ISA and imperative programming abstraction. We then multiply this with a multi-tile abstraction that gives us a lot of parallelism, and add a partition global address space abstraction to access memory. That gives us most of the elements we need. There's another big space to exploit reuse, which we do with two mechanisms we call pre-throw and podcast. So pre-throw is something where you have a tensor or a data structure that's going to be consumed in various other places. We architecturally expose it, and the programmer can tell the hardware that it's doing something that's going to a bunch of places. The analog of that is podcast, which is you're accessing a tensor or a data structure, and the same element is used in many places. You access it once and you proactively send it everywhere, which gives you a huge energy and performance efficiency. So that's kind of out of 10,000 feet, what is the high level ideas in this architecture. So I'll go into an example, which is going to be a little bit low level, but at least I hope to convey some of the elements of what's there and to encourage you to go read the paper. Okay, very simple. Let's start with the blocks, block matrix vector multiply. And the ISA abstractions we have are all data structures are represented as streams. Streams send their values into ports, which are also exposed, and all computation is expressed as a data flow graph. The output of a graph goes into a port, that goes into a stream, which then gets written out into memory. So unlike instructions, register file, control, all of that, all of the abstractions are gone. These are the only abstractions we have at the architecture level. Okay. And then to add this multi-tile thing, so podcast and pre-throw, the idea here is if I have vector, it's being used in multiple places. One access of the stream will send it everywhere. In terms of pre-throw, one write will scatter it to all the places it needs to go. Okay. And at a compiler level or programmer level, this is a program that's kind of like intrinsic. We call it command ISA. And what you're seeing on the far right, and I'm expected to follow all of it, is basically the full program. Parts of it are compiler generated, but this has the abstractions in there in terms of how you express these commands that are accessing streams, moving them into ports, and expressing the work in the data flow graph. Okay. So the gist of our ISA, usually if you have a RISC-V ISA or a RISC ISA, excuse me, you have instructions, instruction format, opcodes, all of that. This is it, what you see on the far right. You have a set of commands, control commands that say how to configure and so on. And then other commands that say where the ports are, what address pattern is needed to access data from those ports. And then the podcasted pre-throw that tell you what the multi-tile reuse patterns are. There are other constants like how many instructions do you have, what is the mix, and then obviously things like the native data path width and so on. So that thing on the far right, half a column of PowerPoint's text, is our precise architectural description. Okay, so that's the architecture. Let's get to the implementation and then the microarchitecture a little bit. So this is the abstract view of the implementation, I guess. We have a bunch of tiles. We have a network that implements this podcast efficiently. We have two HBM2 memories and a PCIe controller. And this was implemented at TSMC, 60 nanometers with the clock frequency of gigahertz and about 400 millimeters square chip. And what you see below are the best eye candy you can get as a chip person, which is die photos and cards and so on. Okay. Hey, Lisa. Okay. Lisa's going to join me in this presentation now. And there'll be a Microsoft portion to it. No. Thanks. Okay. So that's the abstract view. And then my mouse is not working. There we go. Okay. This is a detailed view. I'll spend at most 5 seconds on this. It includes everything you ever want as a chip implementer, all kinds of things like where are the config registers for the PLL, every block you can think of. These are the kinds of things we don't usually care about when we do academic implementations, but these are the kinds of things you have to deal with when you're building a commercial chip and have to get it out there. The paper goes into detail into all of these pieces, and I encourage you to go look at it. Okay, so let's get into the microarchitecture, and that'll lead up to some of these lessons learned. So the goal of the microarchitecture is at every tile to run one data flow graph every cycle. And it has a set of blocks that are shown on the left, and then a blow up of this soft brain module, which is our data flow engine. So it's a tile controller whose job is to orchestrate all of the execution, including some very low level things like mapping of the address space, cache flush mechanisms, and so on. A network controller that implements our 2D mesh, and some other specific optimizations for implementing this podcast and pre-throw in terms of where traffic gets steered. And then the Encore implements the banked second level cache and our synchronization mechanisms and our hardware race-free consistency model on top of the RISC-V instruction set. We have two cores. The first core implements, its job is to execute all of the red command instructions. We had another core whose job was to do other things. We use it to do prefetch, hide the latency and overlap of the podcast and pre-throw traffic as it happens in parallel with all of the computation. Then the soft brain module implements all of the compute data flow pieces within this tile. And that includes two stream engines, and they're essentially hardware structures with some state machine and some buffering to access these various different address patterns, and their job is to hide memory access latency and saturate the memory bandwidth that you have. Then a balance unit orchestrates which of those two gets fed into the hardware array. Then the hardware, the compute hardware or the function unit hardware is called a circuit switch compute array. It's very similar to a CG array. It includes some delay elements to make sure that values arrive perfectly synchronized to give you this nice view of graphs executing every cycle without all of the von Neumann overheads of instruction fetch, register file access, and all of those things. Then we have these input vector ports whose job is to take values that come from these streams and buffer them in a way that when all inputs arrive, they get injected immediately into this array. So that's about my 1.5 minute description of the details of the microarchitecture. I encourage you to go look at the paper, which also talks in detail about 18 further design points that we did and further optimizations beyond the first silicon that allowed us to reduce the power and area by almost a factor of 2. So that's a microarchitecture. And I'll briefly talk about software, and I'll talk about some of the lessons learned. So in terms of software development, we had to write a lot of software, including most of it front end for TensorFlow graph parsing, device-specific graph transformations. We had to redo our own quantization and calibration flow, a runtime library, and so on. So more than 90% of development time was on basically non-interesting, non-novel, non-new things. And then our implementation was a library level thing, kind of like what CUDA does or cuDNN does. The intellectually novel pieces were a stochastic search-based scheduler for DFG mappings. How do you go from the DFG to this nice circuit switch mapping that we need? We had to improve some of our previously published work, which didn't quite scale to the complexity of the network as this network became bigger. And then we had to come up with this visual performance spec so programmers could actually program this thing, which I'll talk about briefly. So we needed programmers to look at this chip, look at some code, and start implementing our libraries. To do that, we came up with this pictorial representation. It does a couple of things. It shows the spatial capacity and the number of units of everything and the communication bandwidth between things. So at a high level, the programmer knows I have 64 tiles. I have 64 bytes per cycle in terms of this podcast ring that allows values to flow between tiles. A layer below, within the soft brain, we expose that you can do one DFG instance every cycle. You can feed constants at a certain rate. And then the commands, the red commands themselves take 3 cycles to execute since they have just specialized RISC-V instructions. So that's a simple piece. There's a layer on top of this, which I'll be very brief. The feed rates of L2 and the prefetch requirements, the prefetch that we can sustain to get stuff out of the HBM memory into the L2. So this kind of simplified picture is all we essentially needed to have non-architect programmers write high-performance code to get our libraries running at relatively high efficiencies. And my point is the balance between the complexity in the architecture and the style of expressing what is in there worked for us. And I'll touch upon this in the lessons learned as well. Okay, so let's talk about performance briefly. First, we got it to work in the sense that we can run the entire MLPerf application suite, which is actually a big deal. Second, we're able to run it at high performance. So here what we have is a comparison to NVIDIA T4, which is again at 12 nanometers. Ours is a 16 nanometer implementation. We're roughly 3x or so faster, and then we also have a 7 nanometer projection. Okay. We also have some data on utilization, which I'll skip over in the interest of time. You can go look at the paper. Talking about the lessons learned, our first lesson is behavior-oriented principles are needed as the primitives for new architectures because applications are changing really fast. In our case, we were able to implement applications that didn't exist when we froze the architecture because we got the right balance of principles versus application targeted features. The second lesson are accessible performance specs are crucial for all future hardware. Our concise pictorial representation work. And my thought here is academic research could formalize this, perhaps with collaboration on software engineering and HCI, kind of in the mold of how coherence protocols and consistency models were developed and formalized by academia very well many years ago. Third, this was a surprise. So the microarchitecture of Dataflow has much to be explored. It was like, oh, Dataflow has been looked at a lot. We thought, oh, we'll just crank this thing out. It was like a ton of design we had to do. And like I said, after we taped out, we felt there was more optimizations we could put in. Like I said, I think there are lots of papers academia could write on going and optimizing various things, and these are all super interesting. Fourth, the software lift needed is extremely large of the non-interesting software pieces. And it continues to be true today. And it's partly because the ML stack is just not modular. And it's not just a compiler needs. You need to fit in this ecosystem, and that's what developers want. Okay. To summarize, Reuse explores Dataflow is a new architecture that provides, we believe, a platform for future AI workloads. And I touched upon some of the lessons learned. And the paper covers the fundamentals of the architecture, more details on the microarchitecture, lots of stuff on chip implementation, bring up validation, and much more retrospective. There are other lessons learned that are not in the paper or in this talk. Happy to talk to you offline, those of you who are interested. And then overall, it was a thrilling journey technical journey to take a clean slate, ambitious design like this and go build a commercial silicon for it. So I'm happy to have shared some of these insights with you. I encourage all of you to go look at the paper and follow up with you for any other questions. And happy to take any other questions.
Thanks, Kar. That was really interesting. Would anybody who has questions please approach the mic and proceed to ask your question?
Sure. Good talk, Karu. I have a question about data flow. Usually at instruction level, it's a mechanism to enable an instruction on arrival of operands. That's how I think of data flow. In the context of your processor, the question has two aspects. What is the unit of computation you are enabling? Looked like it's a task, but I wanted to verify it.
Okay.
And the second aspect of the question is, what is the variability that you're trying to mask by this data flow enablement?
Sure.
Because otherwise you would have gone and scheduled it on a control flow.
Both are great questions. So first is we have two levels of data flow. First, at the operand level, you take something like a matrix multiply or a convolution block, which has adds and multiplies and so on. At that 64-bit or 8-bit operand level, we do low-level data flow execution. A layer above that, this data streams or data structures themselves are exposed in the sense that that's the stream abstraction of inputs flowing into this data flow graph. Okay. Correct. Yes. The second piece, going back to the whole static nature, is since applications are changing a lot and you want virtualized environments and multiple applications and so on, we had dynamic mapping of these streams and how they access memory without statically scheduling the entire thing on this hardware substrate. So that was the other kind of dynamic piece, which is super beneficial.
Nick Lindsay, PhD student at Yale University. So my question is, do you support virtual memory for reasons of programmability, etc.? And if so, why? Or if not, why not?
So do you support virtual memory? And then if so, why not?
If so, why? Or do you? Or if not, why not?
Sure. Short answer is yes, we support virtual memory. And in the sense that we take what is in user land and have mapping of that back into the device memory. So it doesn't have, obviously it's rife with security holes, but those are all we deferred for the next solution. And the reason to support it is kind of without that support, it's simply nearly impossible to support the ecosystem and the software stack that you have. We did what's minimum to kind of get the first solution done.
Okay, thanks.
We'll take one more and then we'll have to go on.
Okay. Sorry, I had a very similar question to the previous
Lisa is the moderator. He may have been here first. But.
Okay.
I think
Okay.
Okay. I guess.
Yeah.
I'm sorry. I'm Karthikeyan from Yale University, working with Abhishek. I had a very similar question to the previous one. I was wondering if you could comment on whether there have been any interesting challenges in supporting virtual memory. You said you take the simplest approach as a start. Has there been any issue in, I don't know, saturating memory bandwidth to the device? Or has address translation been some kind of problem?
Oh, I see. So there are many interesting challenges for virtual memory. In an ideal world, we would do IOMMU like what GPUs do. That's a lot of work and you can get lots of things wrong. We decided that was not necessary.
I see.
We could just get away with a base and bound register, and that's enough to be better than even things like FPGAs, for example, right? And that's enough to move the needle. And then as you go do successive things, you can start doing some of the other more sophisticated issues.
I see. Yeah, I was thinking that because the access pattern seems to be more predictable, it might be.
Yeah, no, at least for us, the data structures are big enough that things like page TLB size and all of those kind of don't become first order issues.
I see. Thank you.
Why don't you go ahead?
Yeah, okay.
Khare, would you
I'll
mind-
wrap
no,
up. I mean, I'll start
unhook
winding up.
so that you
Okay,
can-
it will be a fast question. So, Perry Interfam from Huawei Zurich Research Center. I was wondering if you have tried to consider direct communication between the different types instead of going through the memory each time you want to forward information,
I see.
data between your
Sure.
different types.
So the question is, are we doing communication directly between the types instead of going to
Yes.
memory? So I might have been too flippant in how I was talking about the high level organization. So the mesh network and this podcast ring are designed exactly for that, to send values directly between the tiles. And you go to memory when you finish kind of one operator at the graph level before going on to the next operator. And we were thinking about additional mappings where you could kind of pipeline execution, where instead of the output going to memory and coming back, you're just pipelining between tiles. It's possible in the programming abstraction. We did not do any implementation to see how good that would be.
Okay, thank you.
Sure.
All right, let's thank our speaker one more time. Thank you, Khare. Up next, we have a paper from Meta, a very, very, it seems collaborative work with lots and lots of authors. So it's a big effort. And to present it is Ching-Hsiang on the paper to tell us about software hardware co-design for fast and scalable training of deep learning recommendation models. I think something of interest to many of us. Take it away, Eugene.
Thanks. Hi, everyone. This is Yu Chen from Meta. Today, I'm going to be talking about the software hardware co-design approach that we took in designing the Meta's distributed, fast, and scalable training system for deep learning recommendation models. So this talk, I'll go over a brief introduction to AI at Meta, and then I'll introduce the challenges in training deep learning recommendation models, and then we'll dive into the co-design approach that we took in terms of both software and hardware. And lastly, I will go over some brief results coming from our deployed training system. So first, AI at Meta is basically prevalent and ubiquitous. It happens across many applications and services and at very large scales, driving a large portion of our overall infrastructure in terms of both software and hardware. And the training and serving of AI deep learning models basically happen from data centers to the edge devices. Today, Meta has many data centers globally to serve basically the Facebook.com and our families of apps. And we're also shipping an increasing number of models to the edge devices to provide, for example, augmented reality features in the phone apps and virtual reality experiences in our Oculus product line. This talk will be focusing on the deep learning recommendation models and specifically training because they're used extensively at Meta, and we're seeing deep learning recommendation models are driving more than 50% of the overall infrastructure demand at Meta. So on the right-hand side, we're seeing a chart with the x-axis in a time frame of 18 months. So basically, the overall AI-related data center racks almost tripled within 18 months. While at the same time, the overall number of recommendation model-related AI racks actually quadrupled. And today, we are definitely seeing that the training and serving of DLRM models are one of the largest and most important applications in Meta's data centers. And we absolutely need to do well and perform efficiently on those tasks. So now if we look at what the DLRM architecture looks like, so the first difference that we'll notice is basically DLRM typically takes both dense features and categorical features as inputs. And by categorical features, I mean basically sparse integer IDs as model training data inputs. And the way that we consume sparse integer IDs in the model and let them meaningfully interact with other densely represented tensors is by using a structure called embedding table. An embedding table is basically a collection of embedding vectors, which are basically floating point vectors, representing each sparse input IDs. So by doing embedding table lookups, which is inherently memory lookup or random memory accesses to a large pool of memory, we can eventually convert the sparse integer ID input into a densely represented floating point vector. And then we can use some common deep learning constructs such as concatenation or dot product to interact the densely represented dense features and then densely represented sparse features. And finally, we can use a few MLP layers to get us the prediction of the model. Now, if you look at the DRM architecture from a system perspective, first thing, from the number of a large number of categorical feature inputs puts a stress on the data set feeding part of the training system. And usually a DLRM model requires multiple days or even weeks of training data, and that can go up to tens of petabytes of training data in aggregation. And that requires us to basically store the training data distributedly in a network file system. We cannot afford to store the data locally on the trainer or even near the trainer. So we basically need to have a separate group of machines to stream the data while doing some pre-processing in order to satisfy the I/O bandwidth requirement. And next, since we have a large number of categorical inputs, we also need to have the corresponding number of embedding tables in the model in order to convert them into dense representations. And usually our larger models can have hundreds to thousands of embedding tables, and each of them can vary from a few megabytes to terabytes large. And collectively, all the embedding tables can hold up to trillions of parameters. And the size of those parameters basically dictates that we cannot do data parallel training, which replicates all the embedding tables on each trainer. And here we have to distribute the table or shard the table to each individual trainer to basically store the model states. And next, if you look at the blue boxes in the model, DLRMs do have a few common building blocks in the deep learning world. Basically, the bottom neural network and top neural network are consisting of dense compute modules such as multi-level perceptron or ResNet modules. They are typically compute intensive, and since they don't have many weights, we can afford to train them using data parallelism and use all-reduced communication to synchronize the weights in the backward pass. And one characteristic of all-reduced communication is that it stresses the network injection bandwidth, which means we need to have sufficient in and out bandwidth for each trainer. However, on the other hand, since we're mixing model parallelism on the embedding tables and data parallelism on the dense modules, we have to do some data shuffling once we cross the boundary. And this data shuffling is actually an all-to-all communication pattern. And since there's immediate data dependency on the communicated results, this all-to-all communication actually has to happen on the critical paths of both forward pass and backward pass. And all-to-all communication, unlike or reduce, it stresses network bisection bandwidth. So we not only need to have dedicated bandwidth to each trainer, we also need to have sufficient overall system bisection bandwidth in order to do all-to-all well. So now to put recommendation models into perspective, we compare DLRMs against a few well-known content understanding models. And on the left, we have the comparison in terms of petaflops per second days, which is basically a product of flops per sample and the scale of the data set. And like we mentioned before, DLRMs usually require orders of magnitude higher scale training data sets. And now the fact that DLRM are still comparable to some of the models like BERT and ResNet, that basically means DLRMs can have orders of magnitude lower compute intensity in terms of flops per sample. Whereas on the right-hand side, we have the comparison in terms of number of parameters. And DLRMs actually top all the models that we are showing here in terms of the model size. So combining the two comparisons, training DLRMs actually presents a very unique set of challenges. For example, on each trainer's perspective, because of the low compute intensity, we're going to have a hard time saturating the accelerators. Well, on the other, since there's very large requirement on the aggregated memory size, we have to scale out in order to store the model, which means getting high efficiency from collective communication with a large number of trainers will be challenging. So as a recap, challenges in training DLRM, the first thing is the sheer size of the model requires both data parallelism training and model parallelism training. And both of them actually stress different aspects of the network bandwidth, which means we actually need to provide both. And DLRMs are not all about gems. Other low intensity operators, we also need to do well, especially embedding lookup operations. And since we have a large amount of training data we need to stream in, we need to make sure that the data ingestion is not the bottleneck of training, which Mark will deliver another talk in the 5th talk of the session. So please stay tuned. And typically a system that we design for DLRM will have multiple use cases. For example, offline training, online training, and serving. Each of them will have different resource constraints. So we need to design the system actually against multiple optimization targets. And last but not least, the models and their architectures are changing constantly and growing rapidly. So we almost need to over-provision our system in order to catch the growth in the coming years. So next, let's take a look at our co-design approach in our DLRM training system. So when we first tried to prototype the training system, we basically took GPUs as accelerators and PyTorch as the deep learning framework, which is kind of the popular setup nowadays in deep learning research. So immediately we realized we need to significantly improve the performance of embedding lookup because they were taking more than 50% of our overall training iteration time. And the reason is that the PyTorch embedding back operator isn't all that efficient. It basically launches a chain of CUDA kernels per table, which first thing, it cannot saturate HBM bandwidth. Second, it requires additional memory trips to do backward pass and optimizer update. So we basically went and implemented a set of high performance CUDA operators for embedding lookup and corresponding memory layout changes. We basically did so by fusing kernels and optimizers, so saving one trip to the memory, batching more tables in one kernel in order to saturate HBM bandwidth, and enabling more memory saving techniques. For example, row-wise optimizer and lower precision embedding. And last but not least, we observed decently good locality in embedding lookup operation. And that actually enabled us to leverage not only the fast HBM, but also host memory plus host SSD, which provides us like basically terabytes of storage for embedding tables if those tables are massive in the model. Now, once we have the efficient embedding operations, we took a look at embedding sharding because they are basically being able to distribute embeddings into each trainer in a balanced way is very critical to fully synchronous training. And also because we're doing a hybrid data plus model parallelism training, we need to do two more communication, which is an all-to-all communication for the input and all-to-all communication for the embedding lookup results. So to do that, we actually implemented a flexible sharder that can do embedding sharding along 4 different dimensions, namely table-wise, row-wise, column-wise, and data parallelism, each of them having very different characteristics on the runtime. And in order to do distribution, we define cost functions for each of the steps, and then we can implement placement algorithms to minimize the cost disparities between ranks. And the sharder can serve as the abstraction layer between the model and the underlying hardware that we put together for things like HBM capacity and bandwidth, PCIe bandwidth, and so on. Now, if you look at the hardware that we co-designed with the above software approaches to train the DLRM efficiently, we basically put forth the design of a Ziliang EX trainer node. Each Ziliang EX node is basically an 8 accelerator system. The accelerators are in the OEM form factor, so they don't have to be GPUs. And like we mentioned before, DLRMs don't have high compute intensity. So in our prototype system, we basically used GPUs almost as if they are HBM accelerators to speed up embedding lookup operations. And to do all reduce well, we added dedicated RDMA interfaces over Rongyi for each GPU, and we added sufficient host compute and network for data ingestion demands. And on the right-hand side, we show a diagram of how we connect multiple Ziliang EX machines into a cluster. And we use a hierarchy of switches to provide sufficient bisection bandwidth, so we make sure that we can do all-to-all well. And since Ziliang EX uses Rongyi, it can work seamlessly with the Ethernet network interface that we have in the data center, so we can easily scale out the number of Ziliang EX to thousands. And basically, we have the goal at Meta to deploy deep learning training and inference capacity to the gigawatts level in the coming years. And lastly, I will briefly show some results. There are definitely more details in the paper. Basically, we showed the results from 3 anonymized production models from Meta, each of them having very distinct characteristics. We also show the speedups from various optimizations we can enable on that software hardware system. And we also show the weak scaling efficiency of training a model from various number of GPUs in the system. So to wrap up, we definitely see the performance requirements of training DLMs will continue to go up, paving the way for more hardware specialization and non-standard design. And this is basically because the more complex and demanding models aren't going away, and we need to take a holistic approach in order to have high efficiency in the end-to-end approach. So with that, I'll wrap up and happy to answer questions.
Hi, my name is Gu Yue. I'm from UC Santa Barbara. Thank you for the great talk. So my question is, I noticed that you organized the communication of embedding as 2 all-to-all, 2 rounds of all-to-all communications instead of, I think, as opposed to the natural way to send peer-to-peer lookups and fetch the embedding back. Can you comment on the performance pros and cons of the organizing them as collectives? Yeah.
So basically, all-to-all is implemented using a collection of send and receives. So there's no fundamental system difference between all-to-all and point-to-point communication. And the reason that we want to do basically point-to-point communication in a collective way is because we need to do data parallel training in the upper part of the model. So we need to let them happen basically in a collective way.
Thank you for great presentation. In the paper, so when comparing 8 GPU and 128 GPU, you use the fixed local batch size per GPU. So I wonder the impact of the batch size to the model accuracy. So if you use the fixed batch size per GPU, when we scale out the system, the global batch size is bigger. So I think the model accuracy can be decreased.
Right. So that's basically an evaluation detail. So there are basically different ways to evaluate a distributed system. We can show, so the way that we show it in the paper is basically doing weak scaling of the system. We keep the basically per host workload the same, but then we scale out the system. But from a deep learning perspective, this actually changes the global batch size, as you mentioned. So it will present difficulties in converging the model. So you actually need to tune the optimizer if you're using a different batch size. So if you're coming from the deep learning side of the world, you basically need to do strong scaling in the system. As in you keep the global batch size the same, but when you change the number of GPUs in the system, you'll have to increase or decrease the batch size.
Can I ask one more question? If we pick constant global batch size, when we scale out the system, the batch size per GPU will be decreased. Then as I think when we process the MLP, the GPU utilization is decreased. Isn't it the problem?
Right. So basically, the utilization will be impacted by the per GPU batch size. So that's basically why we decided that we want to go with 512 first, and then see how far we can push that. And definitely we're seeing higher and higher utilization by increasing the batch size. Again, basically 1K will give you higher utilization than 512. Sorry, I actually couldn't hear you well, so not sure if that answers your question.
Yeah, thank you for your answer.
Thanks.
Hi, I am Yonana from Yonsei University. Thanks for your nice presentation. I have a question about the portion of parallelism strategy in the real environment. Can you briefly tell me what percentage of each of 40 parallelism strategy take up on the real server of Meta? Thank you.
Sorry, I didn't get your question. Can you repeat slower? Maybe.
I'm sorry. In the Meta environment, how does the 40 parallelism strategy are? Could you explain the portion of each 40 parallelism strategy in the Meta environment?
I see. So basically, the model has to have certain characteristics when we consider applying one of the four sharding. When we have like models with a large number of embedding tables and the embedding tables are not that different from each other, then basically we can go ahead and do table-wise sharding. And when we have, for example, very tall tables, for example, your sparse ID space has very high cardinality, then you basically consider doing row-wise sharding of the embedding table. And then if you have very wide tables, then you do column-wise. So there are different trade-offs in doing each of those sharding. And a lot of them actually comes from what type of embedding tables you have in your model. Then you can basically explore the solution space and find the optimal one for you. Thanks.
Let's thank Yuchen one more time. For the next talk, we have a talk from IBM. The title of the talk is AI Accelerator on IBM Tulum Processor. And here to present it is Cedric Lichtenau. And I think if you're ready, you can take it away whenever you're set.
Okay, thank you, Lisa. I will not be sharing in Zoom. It doesn't connect over the network. No. All right. So my name is Cedric Lichtenau. I'm the hardware architect for the AI accelerator that we build on the Talon processor. And I will get you through the design and some of the decisions we took there. The Talon processor is the next generation IBM Z processor, which is optimized to run enterprise workload with embedded real-time AI in there. You see on the right side plot, this is a 7-nanometer design with 8 cores running at 5.2 gigahertz base frequency, and features 40% per socket performance growth compared to the previous machine, as well as quantum safe cryptography on the on-chip low latency AI accelerator. This is the bolt in yellow you see at the bottom of a chip that I will be talking about. 32 such.
Okay.
All right, I hope it's better now. Thank you. So 32 such processors are built into an IBM Z16 processor that was announced earlier this year. Before we dive into the accelerator itself, there was a lot of design decision that we had to take. And to go there, first we went to our customers, which are typical being financial institute, warehouse, and other
companies, and we look what is their main pain point when they think about AI and embedding it into their workflow. And it came out that they really want to have inference in their transaction and in real time, so significantly less than 10 milliseconds. And really, all the transaction should be inference with no transaction left behind, also on Black Friday, ideally. And so to satisfy that, we look to have a very large AI compute to process the inference, which is situated very close to the data, which is on the mainframe, and of course having high bandwidth and low latency to access this data. This is what guided us to go for an acceleration, which was memory coherent and on chip or inside the chip. And another dimension is also customers has workloads which are orchestrated, are running on the machine. There's mission critical things with zero downtime. And so we needed to have the AI embedded so that it's not disturbing all their running workload. And this is why we went also for a centralized accelerator instead of putting some AI functions, for example, in all the cores. Also, if you look at the models that they have, they still have a number of machine learning workload because these are very regulated industries, and they're only slowly moving towards more RNN or CNN network. And so we need to provide acceleration covering the whole space of a current workload also where they were moving to. This also dictated, for example, that we needed to pick a format, a data format, which is covering all the space. And we picked up a 16-bit floating point format as the only exposed format of the accelerator. And also the hardware acceleration, we wanted to have it being able to enhance it and change it in the future. So we had to abstract it from the architecture level so that code compiled by the customer could still be running in the future machine. And finally, we had a time to market. And so we pick it up on existing technology, partly developed by the research group in Yorktown, so a few miles up here from New York, and also what we have built in previous accelerators for this system. Design we come up with is this centralized on-chip accelerators I was mentioning, where the accelerators is a first-class citizen, just like any core, is connected directly to the cache hierarchy with over 256 megabytes of cache on each of the chip. So a large footprint that can also be used for AI, but of course should not disturb too much the existing workload too. And the compute capacity, we discussed, of course, long how big should the accelerator be. And we really were guided by what is the transaction rate, what are the models that the customers are planning to run in the next year to size it. And at the end of the day, it was about half the size of a core on the machine. To achieve the abstraction, the architecture abstraction, the accelerator I was mentioning, we added a new instruction on the core, the neural network process assist instruction, which is a memory instruction working directly on the tensor and allowing the accelerator to have direct access to the data, just like the core. There's no data duplication or pinning. And this instruction then supports high-level instruction like matrix multiplication, convolution, or activation, and some combination of this. Diving into the implementation more of the accelerator. First of all, of course, we have pipelined the prefetching. Once you work on this high-level abstraction, like a matrix multiplication, the access pattern to the data is, you can determine it pretty ahead of time. This allows us to fully overlap the prefetching, the execution within the engine, also the write-back. Being connected directly to the internal fabric of a chip allows that to have over 200 gigabytes of bandwidth to access and bring data into the accelerator. Internally, there's a small scratch pad which stores the data that are then distributed by a special data movers engine and formatter engine, which distribute all the data to the compute engine, trying to make sure that every engine has the data correctly formatted ahead of time when compute time starts. The compute is distributed in two different arrays. One array is really intended for matrix multiplication. This is a systolic array with 16-bit floating point arithmetic I was mentioning earlier, doing the heavy lifting for matrix multiplication and convolution. But again, this is only 60 to 70% generally of the model that our customer are running. So if you want to go above 4x performance, you need to also accelerate all the other functions. That's why we have at the bottom, we have further rows of specialty engines, which handles all the other functions very efficiently. In total, each of these accelerators has more than 6 teraflop of performance per chip. And with a full system, you get over 200 teraflop system-wide of performance. To this physical implementation, the accelerator spans 7 square millimeters. It's a high density design. So we have to look at about power integrity. Also, it's located at the bottom of a chip. So there's also some additional power problem we had to handle. And we had to share the area with the chip circuit, which was on one side, you needed to make room for that. On the other side, it allows us to grow a little bit the accelerator during the development and not be bounded to a box very early in the design. And of course, we had a high focus on power efficiency because the AI comes on top for all the traditional workload handle on the core from the customer. About how it was developed, we really worked right from the start in a cross-discipline agile team, so having the hardware development as well as the firmware and the low-level software to make sure that everything works hand in hand and to really have the end-to-end view and the end-to-end optimization. Most of the bugs were still found in the hardware, but we put a lot of effort very early to make sure that we are testing the hardware and at least the firmware together very efficiently. And by doing so, we could squash almost every problem that we have before we had the first silicon. And this has been critical to really squash the last remaining problems and optimization, mainly code optimization when silicon was there and not spend time again to debug the hardware. And I was talking about vertical integration, trying to explain how this is integrated in the flow. If we start with a model at the top of the picture and take, for example, a matrix multiplication, which is available in your model, the first way on the right side is that you use, for example, TensorFlow to handle your model and write the inference. And in this case, we have a device that knows about the hardware and transfer this matrix multiplication into a low-level libraries that talks directly then to the hardware. But as there's many other AI frameworks, we also have the other ways to go through the ONNX, the Open Neural Networks Exchange format, when we can import any model that's be trained on the machine or externally, and run the inference on the machine with deep learning compilers that we have implemented and then using the hardware similarly. Looking at the performance of the instruction. And in this case, we're also accounting for the startup time that we have as we need to call the centralized accelerator. Even if everything happens in firmware, there's still some time needed. That's why you see that for very small tensors, the speed up is not as good as for larger tensors. If you look at the far left, where we have element-wise operation, we can reach up to 5x performance compared to running on a core. And this is due to the fact that we are fully bandwidth limited. Even if we have a large bandwidth on the accelerator, it's not enough for such simple operation. And if you move to the far right, running, for example, matrix multiplication, we reach up to 56x performance improvement, as there we are indeed compute limited. Also looking at the power, I was saying it's very important for the machine for us. So we categorize the power for the various operation, and you see some operation like the max pool has about the same power for all the mover engines and the compute power, the compute engines. And if you go to a convolution, of course, where the compute power dominates clearly the total. We also measured the power over time because we're also worried about spikes. We clearly see, of course, a pattern as we work in tile when computing results and we need to reload weights. This is visible, but was not a problem from our experiment. We also ran end-to-end result using, for example, in this case, a credit card fraud detection model. This is a multi-layer RNN model. And we see that running on one core, this is the blue curve, we have around 1.1 milliseconds execution times and can handle more than 116K inference. And what was requested, again, is this nice linearity. If you run on 32 chips, you go only to 1.2 milliseconds with 3.5 million inference per second still. Similar result was also for machine learning. Machine learning has on top the problem, if you think about the decision tree, it has a very irregular access pattern, which is not very well suited for parallel accelerators. We worked then again with research team to introduce algorithms which are more matrix multiplication based and also saw similar result. If you look at the red curve, we have significantly lower latency and significantly more throughput achieved. In conclusion, the Talon processor is optimized to run enterprise workload with embedded real-time AI inside. We demonstrated first enterprise class server processor with a centralized AI accelerator for low latency transaction inference. Has shown more than 35x speed up for end-to-end AI models run on the machine. We also pay great attention on the vertical stack integration to support a multiple of open source AI ecosystem on top of the IBM AI stack. And the abstraction that we have for our architecture will allow customers to continue running programs in the next machine, even if we decide to enhance the architecture. AI is a fast moving domain or implement function differently. Future works includes optimization further of the model to better utilize the existing hardware, data preparation, which is now a bigger chunk of the transaction as inference is much faster. And of course, looking also into lower precision arithmetic across the stack in its implementation. Thank you with that.
Thank you, Cedric. Any questions, please approach the mics, state your name and affiliation.
Thank you for this talk, Cedric. My question was about the data flow architecture. The improvement that you are actually having is because you are using for the inputs of your matrix seems to be regular. So, for example, for the matmul. So, do you try to execute some application like the inversion, matrix inversion, to see how the data will flow into your data flow architecture? I think that maybe the utilization would be lower, so the speed up would probably drop.
You're talking about matrix transposition, I think, if you're
the matmul.
Format mode, yes.
Yeah.
In this first version, we don't have, we are really focusing on the inference.
Yeah.
So we don't have a transposition implemented yet, but this is something definitely that we are working on.
Okay.
Hello, Cedric. Manoj Kumar, also from IBM. Simple question. How does the accelerator connect to the rest of the Z16 system? Could you say a few words?
Sure. So it's the question was about how it's connected to the system. It's just connected, just like another core. It has the same interface and share the memory. Address translation is not done in the accelerator. We have explained that in the paper due to timeline. This is done on the core by the firmware.
Hi, my name is Hao. I'm from UCLA. So I want to know more the consideration of building a centralized AI accelerator instead of like have a distributed accelerator per core. And also I have my second question is that what is the consideration for placing the AI accelerator at the bottom of the chip instead of like in the middle so that you can have a unified access delay for each of the core?
Okay, so the first question where we did not build it into the core, but had the accelerator separated.
Yeah.
I think the reason for that is that the cores are all running existing workload from customers, which are all very have an access time very sensible to access time. And if we want to stop basically all this work to just run the inference and then restart it, if you have it distributed every place, this would have been very disruptive. That's why we went the way to have this central accelerator. And also, so whenever a core starts it, it has the full power available immediately to himself, basically. Does that answer your question?
Yeah, and my second question is that I think it's related to the first one. So why is placed at the bottom, not like in the middle, like you can have a unified access latency by all of the core, but I think your first question answered that.
Okay, it's placed at the bottom because this is where that was the ideal piece, and I mentioned we can also grow, and we did grow during the design. As we are doing extensive prefetching, this did not tend to be the problem.
Thank you.
Thank you.
Let's thank our speaker one more time. Thanks, Cedric.
All right. Good afternoon, everyone. I'm Jian Chen, and I'm from Alibaba. Today, I'm going to share some of the work that we've done on cloud security, in particular, intrusion detection. Okay. So in the past decades, we're seeing a grand computing paradigm shift that a lot of more and more offline and monolithic applications are moving towards the cloud to take advantage of the elasticity and cost efficiency the cloud has to offer. On the other hand, we're also seeing traditional enterprises and businesses going through the digital transformation to embrace the cloud. And the pandemic only accelerates this kind of transformation. Therefore, the cloud has become the high-value target for various kind of attacks. It is reported that about 20% of all reported attacks are going after cloud. And these kind of attacks includes content-based attacks such as cross-site scripting, IP spoofing, etc. And also timing-based attacks such as distributed denial of service. Now, as the first line of defense, intrusion detection system plays a very critical role to establish a secure cloud computing environment. Now, the intrusion detection system typically sits between the ISP and the CSP's data center, and also sits between the data centers of different availability zones. These kind of data IDS clusters are building on top of commodity Linux servers using open source RDS softwares such as Nord and Saratoga, and doing some kind of mirror or inline processing for signature-based or anomaly-based attacks detections. This kind of system works reasonably well until recently that the network bandwidth outgrows the performance of CPUs. Basically, there is a rule called Nielsen's rule. It says that every year you will see like 50% bandwidth increase. And this rule has been held true until today. And there's no sign of slowing down. But the Moore's law, as we know it, is slowing down. So running IDS over CPU is becoming economically unsustainable. Therefore, it is really absolutely necessary for us to offload some kind of CPU loads, especially IDS from CPU to the hardware. Now, we're not the first to propose this kind of offload, but there are a lot of, although there are a lot of existing solutions for offloading, but there are some kind of limitations. This includes the inflexible software structures. Some solutions, they have a very rigid software structure, and it is unamenable for us to integrate them into our in-house software stack. So that's really a problem. Another problem is some solutions really tightly couple their rules with their hardware solutions. So if it is an FPGA solution, so every time the rule gets updated, you have to resynthesize the FPGA in order to apply the rule updates. So it's really cumbersome. Another thing is about single task acceleration. They only focus on, for example, the regex pattern accelerations. And this single task acceleration has been shown that it's really difficult to achieve line rate processing. And finally, the offloading is really unbalanced. Almost all of the existing solutions are focusing on regex acceleration. And now efforts have been paid attention to how do we prevent DDoS attacks, for example. So the desired offloading solution from CSP is we really need a flexible software structure and swift rule update. These two features is from the DevOps requirements. And also the line rate processing and balanced offloading. This is these are the features that delivering the end business values. So this table shows some of the representative solutions and how they stands according to these 4 dimensions. Now, I would like to highlight 2 of them. One is the Pixels from ISCA'22. Their solution can be considered as a state-of-art solution, but it is really biased offloading only for regex pattern matching. And the Bluefield 2 or 3 from NVIDIA requires some proprietary Docker runtime. And if you look at the DDoS or flow rate classification, they don't have this kind of direct acceleration. You probably need to do some kind of indirect classification using their P4 pipeline. So I've highlighted the background and motivation. For the rest of the talk, I'm gonna walk you through our FIDA solution and the evaluation, as well as some learnings and deployment experiences from the mass production. So FIDAS is our answer to the limitations that I have mentioned before. From high level, it's very simple. So we just put the packet processing, rule matching, flow rate classification in a FPGA. So this kind of FPGA-based acceleration really allows us to define or fine-tuning those boundaries between hardware and software, such that we can ensure the software flexibility. And also we do a lot of rule pre-processing of decoupling the rules from the hardware so that we can ensure the faster rule updating. And also the packet processing ensures the line rate processing. And if you look at carefully, we have rule matching and flow rate classification. Those 2 detection types allows us to achieve balanced offloading. So if we put our solution into perspective, compared to the relatively old technology like GRAX solutions, Pixels versus GRAX, they have improved the solution by achieving the line rate, because they can processing the packet in the FPGA while accelerating the pattern matching. And FIDAS compared to Pixels, we achieve the more balanced solution because we can detect both content-based and timing-based attacks. So this really represents a trend of offloading more comprehensively in the FPGA. Now, I've been talking about a lot about rules. So what are the rules when we're talking about pattern matching? So here is an example of the rules. You can see several keywords here. It's a pcree. Essentially is a regular expression. And you also have content. It's a string pattern. And you can also see that there are some keywords in the regular expression. And there are also substrings in the string patterns. So this kind of forming a hierarchical rules over there. And also you can see that there are rules sort of, contains sub-rules. And this kind of hierarchical pattern will allows us to accelerate this kind of matching. But before we come into that part, let's talk a little bit about how we do this regular pattern matching in full-blown version. So essentially, we're going to do it using the NFA, non-deterministic finite automata. So this graph is a kind of breakdown version of this regular expression. Each state here represents an ASCII code, and along with this kind of graph, you can see we have some kind of bitmaps. So there's shift K bitmap, which essentially represents the states that can make a forward transition with the distance less than K. And also there's an extra transit bitmap here. So essentially the state, those are represented states that you can make transitions larger than the distance of K or make backward transitions. So with this bitmap and the graph here, we can do the NFA-based full regular pattern matching using these kind of steps. First of all, you shift the shift K bitmaps by K distance, and you get a possible successor state with the distance K. And also you use kind of logic OR operations to consider all the backward transitions and also the transitions that has larger distance than K. And final step is you just taking the reachable state and or this end with this successor state to see if the final set contains a final state of an NFA. If there is such kind of final state in the set, that means the pattern has been matched. So as you can see, this step is really not that easy to implement, and it takes quite some resources to do so. So in order to do pattern matching really efficiently, you really need to do some kind of hierarchical pattern matching. As I just mentioned, there are hierarchical structures in these rules. We need to leverage that. So this is an overall pattern matching architecture. So we put a lot of emphasis on rule preprocessing. Essentially, we process these rules in the CPU using some more advanced algorithms to break those rules down into bits and structures that is going to be consumed by the FPGA. So this kind of decoupling structure allows us to do some kind of hardware transparent optimizations and also makes the rule updating very easy. So every time rules gets updated, the intermediate representation of the structures will kept relatively, the structure will be the same, but on the content might be different. So that allows us to do fast rule updating. And also those kind of internal structures where data's contents will be passing through the control paths. This ensures DevOps flexibility. So coming to the hierarchical pattern matching part. As I said, there are keywords. So first, let's do the keywords screening, right? The keywords is relatively short or ASCII words. So you probably have 4-byte keywords over here. And you can do that with some kind of bitmaps. So we have 64 bitmaps over there to do the first level screening. And then once those things get screened out, we check if there are some match on the substrings. Substrings relatively longer, maybe 16-byte long, and we can leverage some more advanced algorithms such as shift-OR algorithms to do more time-consuming matching. And then the next step is to do some kind of rule engineering. We say it's, if you want to match a rule, you have to ensure that all the subrules are matched. So this kind of logic allows us to further screening some kind of packets. And the last step is to do NFA pattern matching. Now let's come into the flow rate classification. So why we need to do flow rate classification? Because it is essential and probably the most time-consuming part of DDoS detection. So we come up with this dual stack memory scheme for flow rate classification. Essentially, we break the DRAM on the FIDAS card into two parts. One is what we call the hot region, and the other is cold region. So for every flow comes in, there is a corresponding entries counting the flow occurrence. So when the flow occurrence reaching to a certain limit, and the cold entry will be migrated to the hot entry, and the empty region will be allocated to a free list. So in the hot region, we can further do some kind of fine-grained classifications. We can do warmer, warm, hot, warmer, hot, those kind of classifications. So each time when a certain threshold has been reached, we can do some kind of swap to making sure that hotter flow will be migrated to the top of this region. So this is a hardware implementation of this algorithm. I will not go into the details. The paper has the detailed descriptions, but I would like to highlight one point here. So this DDoS detection scheme is based on the intervals. So we will monitor the traffic for certain intervals, and once it's reached to an interval, it will update all the stats to the software and resets all the internal structures. So here is the implementation of our FIDAS solutions. We implement everything into an FPGA, and we also did some kind of optimizations, limiting the interface states to 64 states, and limiting the hash bucket size to 6 slots. Now, this solution has been deployed massively in our data center, but evaluating the system on the data production environment is very difficult. Therefore, we created some kind of a controlled evaluation environment. To do so, we have some rule set and traces as listed here. So the results. So overall, as I said, the overall throughput of FIDAS will achieve about line rate 100 gigabits per second. And when the flow contains about 2% of malicious flows, the throughput will be dropped a little bit, because more of the packets will hit to the final stage of the pattern matching edging and require CPU for processing. Regarding the latency part, we can see both FIDAS and Pegasus has very similar latency profiles, and they are all much classifier compared to those CPU-based solutions. Now, on the flow rate classification, we also compare our software classification classifier with one CPU, 8 CPU cores, and for our FIDAS solution, we use one CPU just to analyzing the classification information. So we can see that our solutions, even with 10 million flow rates, we can achieve 0 packet loss. And compared to the software solution, even with 8 cores and even with 200K flows, you can still have like 4.8 loss rate. So significant difference here. So this is basically showing some kind of cost benefit. We're showing using different rule sets what's the CPU core savings we can have using our solutions. And in summary, so this is essentially for pattern matching. We have 30 to 120 CPU cores saved compared to Snort, and plus the flow rate classification, we can save 8 to 12 cores alone. So that translates to, if we're using software solution, we probably need to have 10 servers in order to achieve 400 gigabit per second. But using FIDAS, we only need to have 1 servers with 4 FIDAS cards to achieve that. So that's a significant savings. but compared to BlueField 2, there might not be as cost competitive. But there is one thing here is we can have the full controllability, which is very critical for security applications. So I'll really come to a few experience here. So based on our experience, deployment experience, there is really a synergy of comprehensive offloading. The offloading of flow rate classification improves DDoS detection by 100 nanoseconds. And this improvement allows us to faster removal of the DDoS flows. So that means fewer processing cycles are being spent on inspecting those non-relevant DDoS flows. So which it further improves the regular express matching engine. And DevOps agility is very critical because allows swift rule updating is essential. During the deployment, we've seen like rule updating every day, sometimes every couple of days and weeks. So this kind of a solution allows us to do that. And the final experience is about open software framework is critical, especially come to the cloud security applications. Because software controllability, every CSP pretty much longing for the software stack controllability. If there's something makes you to be vendor lock-in, that's a big no-no. So in summary, hopes I'll convince you that the IDS plays a very critical role to establish a secure cloud, and the existing IDS offloading solutions fell short of CSP's expectations. And our feeder solutions provides balance and synergistic boost to IDS performance while maintaining DevOps agility. So with that, I'll be happy to take questions.
We have time for 1 or 2 questions.
I have a quick question. I'm a software person, so apologize if I didn't get the architecture part right. In the NFA, do you ever run into restrictions where the K states that you have is not sufficient because the fan out from a state is much larger than that? For example, if the patterns are in Unicode or the alphabet size is much larger.
I'm sorry, could you see?
In the NFA, if your fan out is much larger than the K that you had, effectively the alphabet size in the NFA, do you run into limits, or is K sufficiently large that you don't run into that?
So as I shown in the paper, so we did do some kind of statistical analysis. We see that with 64 states, it will cover 95% of situations.
Got it.
So that would be sufficient for us. So the rest of them can be allocated to CPUs. So that's something that this hardware cannot be handled. So CPU can take over. So we should slow down. Yeah.
And then if you're using end-to-end application encryption, how do you deal with that? Because you may not see that at the packet level.
So yes, that's a possible situation. But we are really dealing with non-encrypted the traffic right now. Okay.
Hi, Mohammed Abdel Fattah from Cornell. So really interesting presentation. I was wondering what else from kind of network functions do you want to offload on FPGAs, given kind of the disconnect between bandwidth and CPU power? And what is kind of one missing feature from FPGAs to make them a better kind of network processor?
Right. So essentially, the future we're envisioning essentially align well with the DPU part of solutions. So any kind of infrastructure processing capabilities that need to be offloaded to those accelerators need to be offloaded. But here we are particularly talking about IDS, because IDS is a standalone functionality. It takes its own clusters. But moving forward, the overall structure, you can position this kind of processors, accelerators is kind of DPU. So you can put like security, all those kind of different, encryption, cryptos, decryptions, all those kind of things together. So yeah.
One more, and then maybe you can close your laptop.
Hi, I'm Sihao from UCLA. So I checked the paper, and I have a question in terms of the FPGA implementation. And I found the paper in terms of the utilization of the FPGA resources, it feels like only half of the resources, lookup table, VRAM is being used. Is there any consideration? And you are running at 200 megahertz. Is there any consideration in terms of physical design behind choosing that number and using that much resources, and why you're not using more resources and
right.
higher frequency?
So cutting down the resource usage is essentially something that we think that it's easier for the timing closures. So if you reach into like 80 or even more resource utilization, it's difficult to reach timing closure very fast. So that's one part. The other is packing more functionality into this one. That's a possible solution. Actually, we are doing some kind of future next generation iterations. Maybe consider that. Okay.
All right, let's thank our speaker one more time. Thank you, Jen. Great talk. Oh, your microphone. So that was really great. Thanks. So our next talk is from Meta, and the title of the talk is Understanding Data Storage and Ingestion for Large-Scale Deep Recommendation Model Training. I think you have mentioned that to stay tuned for this talk, and I guess Mark is going to present that. So here we have Mark Zhao, who is a visiting researcher at Meta in FAIR, where he is currently working on production infrastructure for ML training at scale to present this talk. Mark, go ahead and take it away whenever you're ready.
Thank you so much. As Lisa said, if you weren't here for Yuchen's earlier talk, I encourage you to take a look at it since it will give you a pretty complete view of how we do ML at Meta. So today I'm going to be talking about how we store and ingest training data for large-scale deep recommendation model training at Meta. This was done in collaboration with a ton of really great people, and I just have the honor and privilege to present it today. So machine learning is used pretty extensively at Meta across a variety of products, but perhaps the most dominant and prevalent use case of machine learning models are deep learning recommendation models. And so these models are used to suggest like new and meaningful content for users, and as a result, underpin a lot of our products. For example, Instagram Reels or newsfeed post ranking. As a result of their prevalence, they actually require a majority, as Yuchen said, of AI training capacity across our fleet. So again, we're building data center scale AI training clusters and multiple of these across the globe to support this really intense demand for capacity. But what I want to talk about today is that these training clusters are more than just accelerators themselves. They're more than just GPUs, right? So if we kind of level up a bit and take a look at what the end-to-end production ML pipeline looks like at Meta, well, we first start with this data storage and ingestion component, right? So here we store data, and then during training, we do some pre-processing to it to generate tensors. Secondly, these tensors are then loaded into trainers, right? So we're constantly launching multiple training jobs across a variety of model types. And then these training jobs produce models that are then sent for evaluation. So depending on the evaluation results, the best performing one will typically get deployed into production. And then we serve inference requests from our production model, right? These inference requests are then used to generate more training data, and the cycle continues. But what I want to focus on today is this first component, the DSI or data storage and ingestion pipeline. And it consists of three main things. So data generation, storing it in a distributed manner, and then online pre-processing during training. First, let's ask, why do we care about DSI, right? And the fact is that DSI represents a significant component of our training capacity fleet-wide. So what I'm showing here are three representative recommendation models, arms 1 through 3, and a breakdown of their infrastructure power requirements split by storage, pre-processing, and training. And what you can see here is that the DSI component, the storage and pre-processing, takes up anywhere between 1/3 to over 2/3 of our power capacity within our data centers. But compared to these trainers, the red portion, DSI is pretty understudied. And that's what we're trying to address with our work, right? Is to really understand and characterize what DSI looks like at scale. And so for the rest of this talk, I kind of want to synthesize our characterization results around asking 6 main questions on what are some of the key research and design issues and questions that we have from our experiences building a DSI system. So naturally, the first question is, well, yeah, how do we build an industry scale DSI pipeline, right? Let's start by looking at what some of you guys might be familiar with in cases like MLPerf, where we start with a static data set, like the Criteria data set or ImageNet stored in the cloud, right? And then we might want to use something like an NVIDIA DGX machine to train the model. And we first start off by just downloading the data set to local storage. And then offline, we might run some pre-processing on this data set. And then now we start the clock, right? And then during training, we use the host CPU to read batches over multiple epochs from local storage. You might do some more pre-processing like crops to it, and then load these pre-processed tensors into the GPU for training. We'll train until convergence, right? But this setup doesn't really work in our environment, and I'll go through a few reasons why. The first is, well, if we just look at the simple data set size here, what you can see is that our recommendation models take up anywhere between 2 to 26 to even more petabytes of data set size. And we only read these over a single epoch, and as a result, we can't store these data sets locally. Next, let's look at the pre-processing requirements. What you can see here is that during training, what we need is between 10 and 55 x86 sockets per 8 GPU node, right? And so I'll go into details of why this is so expensive, but you can imagine that if we have something like 2 or maybe even 4 socket machine, this isn't viable. So the implications of this is if we were to do everything within a single box, this means that we would run into significant underutilization of our GPUs, just simply stalled waiting on data to come in. So this is a really important problem to address. Right, so the takeaway I want to emphasize here is that we really have to disaggregate our DSI resources in order to scale them to meet the really diverse demands of our models and training jobs, and as a result, eliminate data stalls. So now let's take a look at what kind of DSI looks like at Meta, right? So there's 3 main components. The first one is the storage tier, and we have one of these per data center. The storage tier first consists of kind of a continuous data generation pipeline. So these are your streaming and batch ETL jobs like Spark that take raw event logs and then join them, pre-process them to generate structured label training samples. These samples are stored in Hive datasets, again, petabytes large, which are then broken up further into structured columnar files within a distributed file system that we call Tectonic. Next, for each training job, we actually launch a cluster or a set of DPP workers or distributed pre-processing workers. These are stateless workers that live throughout the entirety of the training job and do 3 main things. First, they read data, right? So they read data from our file system and reconstruct rows from it. On top of that, they do filtering and they throw away unused features that live in the data set but aren't used by the model. Secondly, they apply a lot of transformations to these raw rows and as a result generate tensors. And finally, these tensors are then loaded into a trainer tier. And so this trainer tier is what Yuchen talked about with our Zion EX nodes, for example. And we have multiple of these running for each training job, right? An important thing to note is that we are continuously launching and running a mix of diverse training jobs across different model types, all of it on shared infrastructure. Okay, now that we've seen kind of what the pipeline looks like, the obvious next question is what bottlenecks exist here. And it's important to really understand these bottlenecks because if we're able to kind of address them and improve the performance and efficiency of storage, of readers, well, then we can devote fewer resources to eliminating these data stalls, right? And going back to the beginning, what I mentioned is we'll have more power capacity for trainers. So really the goal here is kind of to shift this balance of power more towards training, and we'll have more resources to train models with. Okay, first let's look at the reader tier. So what I'm showing here is the resource utilization at each reader worker running for each of our models here. So you can see that RM1 is bound on CPU utilization, RM2 is constrained on network utilization, and RM3 is constrained on memory capacity. And so, I mean, the takeaway here is that we have a lot of diverse bottlenecks. But on top of that, as we're looking forward into the future of our what our general purpose compute nodes are going to look like, we see that compute and network capabilities are outpacing memory bandwidth. So on top of that, we think that memory bandwidth will become a dominating factor here. And just to give some ideas of what we need to address or what the community needs to address for the future. So next, let's look at the storage tier. So if we just do some back of the envelope calculations here, we need to store on the order of 100 petabytes of bytes per data center and serve them at on the order of 10 terabytes per second. And it's not just sequential read bandwidth, right? As I mentioned earlier, we do a lot of filtering and we store data in columnar files. What this means is that we have pretty small IOs. So if you combine all of this together, we're actually very IOPS bound on our hard drive based storage tier. This means that we have to actually buy 8 times more storage capacity in order to supply the IOPS that we need from our storage tier than we need to actually store the data set itself. So there's this big imbalance here. Okay, we've seen the bottlenecks. How do we address them, right? Well, if we go back to the storage tier, what we think is a promising area is leveraging application characteristics, right? And we're leveraging the fact that there is data reuse across training jobs for a given model type. So what I'm showing here is across our 3 recommendation model types. On the x-axis is a storage CDF. What this means is that the X% of the most popular bytes within our data set contribute to, on the y-axis, Y% of storage IOPS. So just to give a concrete data point here, for example, if we look at 0.4, what this means is that 40% of our bytes in storage contribute to over 80% of our IOPS from storage across our recommendation model data sets. And you can imagine that there's an obvious opportunity here where we use heterogeneous and hybrid storage devices, such as leveraging Flash for this frequently used data. And we're taking advantage of the fact that SSDs offer higher IOPS per watt versus hard drives. But there's a lot of challenges here, right? That we talk about in our paper, but just to give a high-level idea, we read data over a single epoch, so we use this across training jobs. We need to predict really these diverse feature sets, et cetera. But the takeaway here is that we have a lot of opportunity and challenges to use hybrid storage to balance throughput and capacity of our storage tier. Next, let's look at the reader tier, right, for online preprocessing. And the obvious thing that comes to mind is, well, if we use accelerators for training, why not for DSI? And there's 2 areas that we think this could be applicable, right? First is data transformations. So the table to the right is showing just a list of some common preprocessing transformations that we use for DLRMs. The other area that's been talked about a lot in recent work is just standard data center operations. So just reading data from storage and loading these tensors to the trainer node. So there's a lot of data center tax overhead that can be potentially addressed here. Of course, there are challenges. These transformations are pretty diverse. They're not just general matrix multiplies. And so a lot of them have different amenability for acceleration than others. There's other challenges, again, that we elaborate on in the paper, such as where to put this accelerator and other issues such as kernel launch and memory management overheads. So again, the takeaway is accelerators are great and there's lots of opportunity for them, but potential challenges that need to be addressed by researchers. So now that we've looked at the hardware in isolation, let's think of what challenges arise when we try to combine them and build a data center for ML training. And the main thing that you can kind of see from the previous slides is really diversity, right? So across our recommendation models, we have really diverse storage requirements, really diverse preprocessing requirements that need to be addressed. There's 2 other dimensions that we need to think about too. First is time, right? So on the chart to the bottom, I'm showing over the course of a year, the aggregate compute demand for training jobs across our fleet. And what you can see is that there's very distinct peaks and troughs corresponding to different phases of our model release cycle. So we need to manage and split resources to supply this need. The other dimension is space, right? We can't just put a huge cluster in one data center. We have to build multiple data centers and distribute them around the globe. So naturally, a question of scheduling comes in. So the takeaway here is that we have to really think of how to design data centers to really address these diverse and intensive workloads. But at the same time, we think there is a potential for optimizing ML schedulers and co-designing them with our data centers to improve the overall resource efficiency across our fleet. So it's now that we've talked about the hardware and the data center, it's also important to look at the software and ask how do we improve the efficiency of the software. And there's 2 dimensions here that we think might be useful. First is top to bottom, right? And this is your traditional hardware software co-design where we try to understand what the application looks like, how it behaves, and try to optimize it for the underlying hardware. So an example of this that we talk about in the paper is we leverage the fact that certain features are more popular than others, and we reorder how we write these features to group those together to increase our disk IO size, which speeds up our storage tier. The other dimension that's maybe a little bit less considered is end-to-end. So we have to really view this entire DSI plus training pipeline as an entire entity, right? And be able to trade off efficiency and optimizations across this pipeline. So just another example in our paper, we talk about how we added additional metadata to our file formats, which increased storage overhead. But by doing so, allowed us to push filtering from readers to storage, which significantly saved power. We talked over a few other optimizations, but in aggregate over the past few years, what we've seen is these systems optimizations have resulted in over 2.6 times power savings, which, as I mentioned in the beginning, have really been impactful in allowing us to provision more training capacity in our data centers. So the takeaway here is that systems optimizations are important, right? And we think there's two potential dimensions that they need to be addressed: top to bottom and end to end. Okay, so I've talked a bit about kind of what research problems, what challenges we've seen from our experience. Maybe the broader question to ask is what do we need as a community for further research in DSI, right? And you can imagine that the biggest challenge is really this disparity of what I talked about in the beginning between an academic and industrial DSI setting, right? Something like MLPerf, where we use a single box or maybe a few training nodes, looks pretty different from what I showed at the beginning with our entire DSI pipeline. So the main takeaway here is that we need ongoing and continuous work between academia and industry to really build representative industry scale benchmarks and systems for more research, further research on DSI. I won't go into the details of these specific projects, but just to list out some of the efforts that we've recently been involved with. I encourage you to take a look at these and contribute if you have time. So just to summarize, I want to close by saying that DSI is a really fundamental and significant component of our overall ML training infrastructure, right? We really need more research towards efficient and performant hardware, software systems to continue scaling our infrastructure into the future. And yeah, thank you for your time and happy to take questions.
Thanks, Mark. And in the interest of time, we'll just take 2 questions. Go ahead.
I'm Thiruvengadam from NVIDIA. I noticed that in one of your early slides, you said that your pre-processing needs were so high that just a 2 or 4 socket thing won't work out for you. And in a later slide, you said some of them could, yes, be accelerated, but some of them could not be. So I think the number you said, instead of 2 or 4, was some number awfully high. I don't remember where it was.
Like 10 to 55, yeah.
Right. So where does, let's say you assume you can accelerate whatever you can accelerate. What does that number look like? Is it closer to 2 or 4? Is it closer to 55?
I honestly, that's still a very open resource question. I think going back to what Yushin talked about earlier, where our models have pretty lower arithmetic intensity than vision or NLP model. And that's one of the main areas of why we see so much more requirements. But there's also issues with kind of a production environment that we have to deal with, like TLS encryption, which adds overhead, data reading, and all these libraries just to have a workable production environment that adds some of these complexities. So I think in terms of how much this reduction can be, will vary by model. I don't think we have a clear answer of exact number of you need 2 sockets or 4 sockets, but I'm hoping that more characterization will be done on the specific operations to kind of answer that question.
Okay, thank you.
Hi, I'm Michael Wu from Yale University. I had a question. So you mentioned that before the training even starts, there's this huge kind of storage and processing overhead. And then Yushin also mentioned at the start of training or each iteration, there's kind of another storage thing regarding the embedding tables and stuff.
Yeah.
I was wondering and maybe I'm misunderstanding the relative scale, but I was wondering if there's been any interesting work in perhaps integrating the two. So what if you kind of overlaid that kind of memory lookups with the other storage things or?
Yeah, that's a good point. So I think the storage requirements that I talked about in this talk were for training data. So the training samples that come in, and what we do with that training data is pass it to embedding tables, which is what Yushin talks about, where we kind of map the training data from a high dimensional space into kind of a dense vector, which is what the embedding tables are. They're simply lookup tables for training data, right? Yeah, I definitely think that you bring up an interesting point on how to kind of co-design these. I don't have an answer. Like, I think it's cool and interesting, but I don't, yeah.
Thank you.
Thanks.
Let's thank our speaker one more time. Okay, while Dan gets set up, I'm going to make a quick announcement. Did anybody lose a ring in this room? Okay, if you did lose a ring, you can describe it or come up to me and describe it, and if it matches, I'll give it to you. Otherwise, I will be giving it to Lost and Found. All right. So we saved the best for last. I mean, consistency models are the easiest thing in the world to understand, and that's why we have it at the very, very end of the day. Sorry, Dan. So we have our last talk for the day, which is Dan Lustig from NVIDIA to talk about mixed proxy extensions for the NVIDIA PTX memory consistency model. Again, not mind-bending stuff. Dan Lustig is a member of NVIDIA's architecture research group. He mostly works on GPU memory system architecture and memory consistency models, everybody's favorite topic. Before joining NVIDIA, Dan received his PhD from Princeton in 2015. All right, take it away, Dan.
All right, thank you, Lisa. Yeah, so thanks everyone for sticking around. I know it's the last talk of the day. It's a long day, so I'll try not to bore you with lots of low-level complicated memory model details. But today what I want to talk about is the high-level direction that we're going with NVIDIA's memory consistency model, trying to integrate more accelerators and more special purpose features so that we can keep scaling into the future. So with that, let me click here and then we can dive in. So first, let's remember what a memory consistency model is. It's the values that loads are allowed to return from memory, and obviously a widely studied topic over the years for CPUs, for GPUs, a little bit for accelerators even. And so part of the goal here is to bring a lot of that together and figure out how we integrate these into a single system. Because if you look at a modern GPU, it's a lot more complicated than it used to be. It's not just a general purpose machine anymore. I mean, we put a lot of effort into making these machines general purpose, but now we're also mixing in these accelerators and special purpose features. And so if we want to put them into the programming model and into the memory model in a way that's forward compatible, we have to figure out all the details of how they actually do integrate and how they interact with memory. So that's what today's talk is going to be about, understanding what memory looks like on modern NVIDIA GPUs at least, and then understanding the solution that we came up with, which we call proxies, which is a general purpose abstraction for a lot of these different accelerators. And I'll get into that towards the end of the talk. So let me start with a little bit of recap. So this is what a generic traditional view of memory might look like on a GPU. So up at the top, we have these SMs, the streaming multiprocessors. That's where the cores are. Each SM has an L1 cache. Those L1 caches are connected to some big on-chip interconnect, which is in turn connected to a big L2 cache and memory, and also connected to PCIe or NVLink or some other interconnect to talk to other devices in the system, CPUs or GPUs. And again, this has been widely studied in prior work. Architectures that look like this for GPUs. We've seen scoped memory models. We've seen arguments against scoped memory models for those of you who are familiar with that means. We've talked about our specific instance of this at NVIDIA in Asplas's paper in 2019 for NVIDIA PTX. PTX is the virtual ISA and portability layer that we use for assembly across different architecture generations. So this part is widely understood. We're not changing this. We're not canceling this out. But what we're doing is taking this as our baseline and trying to integrate all these accelerators that I've been talking about into a system that looks like this. Because, as I said, we're moving beyond the traditional view of memory. So that type of system that I just showed on the previous slide, we first formalized that along with our Volta architecture, which came out in 2017, and the paper was published a couple years later. That's our first general purpose system, but our first truly general purpose memory model in the sense of having a modern understanding of what memory models are, threading a model, and so on. But since then, and since the development of Volta, I don't think this will come as a surprise to anyone in this room, but a couple of big trends, I guess, have been happening. Right, we're moving into a post-Moore world, so we can't always keep scaling general purpose performance and power and area and so on, all the favorite metrics. We can't keep scaling them as easily as we used to. We're certainly not getting as many transistors as we used to for free. And so we turned to things like specialization to try to recover some of that performance scaling that everyone's come to expect year to year. And in particular, one of the hot domains, obviously, these days, machine learning, deep learning, and so on. And so that's what motivates us to keep putting in a lot of these special features for tensor cores. I'm sure a lot of you are familiar with tensor cores on NVIDIA GPUs, accelerators like that. And we have tensor cores, we have texture caches and other special features for graphics. And who knows what we're going to have in the future, right? Things keep evolving, sometimes very quickly. And so what we want to do is figure out kind of a general purpose model for incorporating special purpose features, which is kind of a little bit of an oxymoron, right? So the more specialized it is, the harder it is to generalize, but that's fine. We want to try and find that sweet spot that gives us a kind of a common model for all these different accelerators, but still lets them get all the efficiency that everyone's looking for out of accelerators. So that's kind of the general research question that we're going for here. So I'm showing Hopper here on the right. That's our newest architecture generation. And let me zoom into a picture of what memory looks like on NVIDIA Hopper. So this is a slide I borrowed from a GTC talk earlier this year. This is actually new information that has gone out publicly since the release of the paper itself. So this part itself isn't actually in the paper. So there's a bunch of stuff going on here. I'm not going to go into all of it step by step. You can refer to the GTC talk for the details, but what I'm going to do is break it into pieces, right? So this piece on the right, that's the slice of the traditional memory picture that I showed a couple slides ago, right? We have the SM at the top, we have some other things, we have the L1 cache, connection down to the L2 cache, and memory down at the bottom. But what we also have in the middle here is a whole bunch of other new pieces and special pieces, right? Non-standard types of things. So I mentioned tensor cores, which are kind of widely known at this point, I think. But what's probably not as widely known is this new unit, which we call TMA, Tensor Memory Accelerator. This is a new accelerator, not for doing the tensor computations, but for feeding the tensor accelerators, right? We have to pull data in from memory and feed that into the tensor cores. And that itself can be a hard problem sometimes, right? So what we built this accelerator, but obviously we want it to be efficient so we can keep our overall throughput high. And so what we did is not kind of build this in line with all the traditional view of memory and the traditional path to memory, but it's sitting here off to the side. It's kind of a special path. You can see it's obviously a cartoon picture, but it's not really going directly through the L1 cache. It's kind of sitting off to the side. It's doing this kind of special synchronization. You can see these transaction barriers that are happening asynchronously. Again, I'm not going to go into the details of what exactly that means, but all this is happening through special purpose SM to SM network, which is not something that used to be there, right? So there's a lot of new stuff that's going on that is exactly the type of thing that we want to try to understand when we put this into our programming model, because we want people to be able to use tensor cores today. We want people to be able to use those same tensor cores and tensor memory accelerators in future generations without breaking backwards compatibility, right? So we have to think outside the box of what memory traditionally means. We have to think of all of these things that are interacting with memory as also being part of the memory subsystem of the GPU now. So let's take a look. Let's go back to kind of a cartoon picture again to understand what the behavior is of these different accelerators or special features that we're trying to integrate, right? Zooming back out, obviously, again, reality is much more complicated than this, but this picture is going to be enough to understand the gist of it. So same general picture as before, SM, on-chip interconnect, L2 cache, but this time next to the L1 cache, we're going to have some box that we're going to call either an accelerator or a special purpose cache of some kind, or maybe both. Maybe the accelerator itself has a cache hierarchy. These things maybe aren't fully coherent with each other, right? It's going to depend obviously on what accelerator or what cache we're talking about, which implementation, which architecture generation we're talking about. But the general model is, for the moment, let's assume there's not really strong coherence between these two different paths. And so once you start building an architecture like this, it's not hard to figure out the types of things that can go wrong, right? If we do a store down one path and we have a load down a different path, they can either get reordered with each other, so they go out of order, which is unexpected, especially when it's accesses to the same address, or maybe that load's going to hit on a stale value that's stored in the accelerator's cache because the store going through the L1 cache didn't update that stale copy, right? There's all kinds of things that can go wrong compared to what you normally expect from memory behavior. And so in particular, even in a simple example like this with a store followed by a load, we can have now the notion of an intra-thread data race, which seems like a bizarre thing, right? You usually expect that single thread code is not really subject to weak memory model behavior. But for the direction we're going, when we have these accelerators and special caches sitting off to the side here, and we want to build these things for efficiency, you can have the notion of an intra-thread data race, as bizarre as it sounds. And obviously you can still have inter-thread data races as well, right? So we have to understand that, we have to accept that if this is the architecture that we want to build. And then we have to figure out what synchronization mechanisms we want to put in place in order to restore the ordering when we need to. And again, same concept here holds whether it's texture caches or constant caches or accelerators with caches. There's all kinds of different stuff on the GPU. Even virtual aliases kind of behave this way, right? If you think of two different virtual tags as kind of behaving the same way as if they were different caches, right? There's a lot of different features. And so that's actually what motivated us to kind of think of this as not just here's the model for accelerator X, here's the model for accelerator Y, and so on, but instead to try to come up with a common abstraction for all of these different things. And that's what we call the proxy memory model. Right, so before I get into that, I want to step back and have maybe a little bit of a controversial slide, we'll see. Right, so why not just forget that whole design that I just showed you and say that's a bad idea? Why not just make everything fully coherent and simplify our lives, right? For sure, it would make the model, the complexity a whole lot simpler, a whole lot easier if we didn't build it that way. We just kept everything nicely in line. We kept everything coherent. It would make the programmer's life simpler. And so no doubt about that. What I want everyone to understand, though, is that it does come with cost to do it that way, right? You're going to have the complexity. You can bury it somewhere. You can bury it in the memory model. You can bury it in the implementation, but it's got to be somewhere, right? So everyone likes to talk about the performance implications or maybe the power implications of memory models, and whether weak memory models allow you to get more performance. Right, that debate's been going on for a long time, but I want people to understand also that there's other costs associated with this as well, right? We have area can be a cost, design and verification costs can be actually a pretty big thing. It's not always the most important metric when you read academic papers necessarily, but from an industry deployment perspective, it's actually pretty non-trivial costs that we have to understand, right? Sometimes it would be, or often it would be harder to integrate these things, or often it's hard to integrate a aggressive cache coherence protocol of some kind that's not going to get in your way in terms of performance. The other big bullet here is future architectural flexibility is another big one, right? Maybe we could find some microarchitecture that lets you design an accelerator with coherence, with great performance, power, area. You can spend the cost to design it, but then if you do that, you're locking yourself into a strong memory model, perhaps for as long as this feature shall live, which can be a long time. Right, so future architectural flexibility is actually a pretty valuable thing that is, I think, also a little bit underappreciated when people are designing these things. So the proxy memory model is designed to, or is willing to accept this increase in complexity in the programming model in order for us to deliver better performance, power, area, or even sometimes just make it better or easier for us to deploy these things and get them out into the world faster. So let's take a quick look at the proxy memory model. A proxy now is an abstract label that we apply to each kind of memory access. It's not a physical thing. It's not a concrete thing. It's just a tool that we use to label all these accesses that are floating around in order to do our analysis on what values we expect to come back from memory. So if we do a regular load, a regular store in this case, we would say that's performed via the generic proxy. But if we do a load.constant, in that case, it would go through the constant cache. We're going to call that the constant proxy. And so when we have these different proxies floating around at the same time, that's when we start getting this notion of a data race or even an intra-thread data race, depending on what test you're actually running or what program you're actually running. And so we also introduced this notion of a proxy fence, which is the mechanism that lets us restore the ordering that would otherwise not be enforced, right? It will flush out any non-coherent caches. It'll flush things far enough down the pipeline and whatever else it needs to do in the implementation in order to fix the ordering that you might expect from a store followed by a load to the same address. And so that's the general notion of what a proxy fence is and how it works. regardless, again, of whether this is constant caches or tensor memory accelerator or whatever other special feature we want to incorporate. And so we have a general purpose programming model here. The paper goes into a whole lot more detail than I'm getting into in this talk now. But so the general model in 2 bullets, the programmer is responsible for putting in these special proxy fences whenever they're using one of these special purpose features. So this is all opt-in whenever using the accelerators. The baseline memory model is not affected. And these proxy fences and synchronization in general are also, as you might expect, designed to nicely and compose with each other cleanly so that you can wrap these things in libraries, put them in, build up larger synchronization patterns and write your larger programs. So in a very quick nutshell, that is the idea. The paper obviously goes into a lot more detail. Like I said, it has a formal axiomatic model in there of the kind that is used for modern memory models. It's got an English specification as well. And this notion of proxies is partly deployed in PTX today. If you go look at the documentation online, you'll see it, or at least the first pieces of it. And maybe you'll see more of it emerging over time for some of these other new features that I talked about. So in conclusion, we're in this post-Moore world where we need to start integrating, or at least we want to start integrating more special purpose features and accelerators and caches and so on into our general purpose programming model, into the memory model for PU. And so people have paid a lot of attention into designing the accelerators themselves, but we also have to understand how to feed these accelerators and how they interact with each other, with the different threads in the system, and with memory. And so that was the goal of the proxy memory models, to give us a rigorous but still flexible way to understand how to integrate all these different kinds of accelerators in a common way to the memory model for GPUs. And so that is proxies. Thank you.
Hi, I'm Romano from Cornell. Is there a particular reason why the proxy doesn't fence by default? Why does the program have to declare it as opposed to just it being fenced and you declaring a non-fenced version?
Right, good question. So the biggest reason is that the proxy fences are not free, right? If you think back to that picture with the different paths, the implementation of the proxy fence might be to flush things down the different paths and flush out old incoherent lines that have gone stale. Right, so if you put that in by default, then you're gonna have to pay the cost of that synchronization by default. And so the model is more crystal ball and try and predict the future of what accelerators we might ever want to build as far as we can see, which is obviously kind of a tough thing. But what we think we designed is a model that's general enough, at least to capture these types of accelerators that are kind of in this domain that I mentioned that I showed of like kind of near the SM, not necessarily super far away, not like on a different chip or anything, but close enough that you can synchronize when you need to without tremendous cost. But still gives them enough leeway to go and do their own thing. Like we have, like I mentioned, the texture caches, the tensor cores, tensor memory accelerator. There's a bunch of different, we've had a bunch of different features that we've managed to integrate into this model so far that gives us some amount of confidence that it's general purpose enough for, at least as far as we can see, into the near medium term future.
So complex topic because I'm not an expert in memory coherence, but it seems like proxy is just a way to ask the programmer to classify data so that he can put it in differently designed caches, and you don't want to manage coherence between them. Therefore, proxy fence is another capability that you give to the programmer to enforce coherence where you need it, where the correctness of the program needs it. Is that a correct understanding of the whole approach?
Yes, that's a good summary. Exactly. You pay for coherence, you pay for synchronization when you need it. And when you don't need it, you're allowed to take advantage of the whatever extra performance, power, energy, efficiency that you might get.
But
yes.
The burden is now on the programmer.
Yes. Exactly. The trade-off slide, exactly. You're paying a little bit of complexity, but you get hopefully a little bit of performance back. Yes.
Hey, Dan. Great talk. Nick Lindsay, Yale University, PhD student. So I guess my question is, well, first a comment. I think the solution you've got is really cool. I think it makes a lot of sense. But my question is actually kind of relating to axiomatic versus operational models. So your definition of an operational model was very intuitive. And it looks like you've actually managed to integrate it axiomatically very nicely. But I'm wondering if you expect, as you add features to the axiomatic model, whether you expect it's going to be harder to map operational models to the axiomatic model, and whether that's going to present complexity challenges when it comes to actually formally verifying hardware.
Good question. So brief one sentence recap for people who aren't familiar with the terms. Axiomatic models are everything is permitted unless there's a rule explicitly forbidding it. Operational models is more you build kind of a abstract golden model of the microarchitecture, and whatever you can get from that golden model is the set of legal behaviors for the system. And so modern memory models try to find a way to get those two different approaches to meet in the middle somewhere, and that's when you know you kind of have a good sound memory model. So we use axiomatic models because we kind of like that approach of everything is permitted unless otherwise forbidden, because it gives us the most architectural flexibility. And like I mentioned, that was one of the big metrics that I think is valuable to us, at least, is the ability to change the implementation in the future. Because this is a fast moving field. We don't necessarily know what is going to be in demand next year, the year after, right? So we do our best, but almost certainly it's going to change from year to year. And so we like the axiomatic models because it gives us, like I said, that most flexibility